Hi, this is an example problem having to do with calorimetry from chapter 12. Pause for a moment and read the question. So in this problem, we're going to have some coffee that's hot. We're going to add cool water to it, and we're going to wait until they come to a final equilibrium temperature. Now we're going to assume that the cup is insulated and it has zero specific heat, so that the transfer is solely between the water and the coffee. And in that case, we have two objects that we need to be concerned with. We've got the water and we've got the coffee. And for each of these, right, this is going to be between the range if we draw a temperature scale here. The water is going to start at 15 degrees Celsius. The coffee begins up here at 86.7 degrees Celsius. And then we already know what the equilibrium temperature is going to be right here. They're going to mix, exchange heat until T final for both is equal to 57.2 degrees Celsius. Now within the range 15 to 86.7, both water and coffee remain liquid, and so we're going to be able to use the delta Q C is equal to the mass times the specific heat capacity times delta T. And so we want to know what M for the water is, C for the water, and delta T for the water. And the same thing for the coffee over here. Now let's see, for the water, how many kilograms must be added? We don't know what that is. This is what we're looking for right here. For the coffee, it's 0.145 kilograms. The C values given for both of these, and since coffee is essentially almost like water, we're going to use the same value of C for the coffee as we do for water. And finally, we can do some calculations here, right? So for the water, the temperature is, right, the final 57.2 degrees Celsius minus the initial 15 degrees Celsius. That gives us a value here of 42.2 degrees Celsius. And for the coffee, we are going to have a final value of 57.2 degrees Celsius minus initial value 86.7 degrees Celsius. And that gives us a value of minus 29.5 degrees Celsius temperature change. Now, calorimetry, no heat is lost from the system, so the sum is going to be 0. Here we have a QC for the water plus a QC for the coffee. They sum to 0. So we've got mass of the coffee times specific heat of the coffee times delta T for the coffee plus mass of the water, specific heat of the water times delta T for the water. They sum to 0. And we know all of these things except for the mass of the water. That's what we need to solve for. So before putting in any of the variables, let me go ahead and we'll keep this guy here. And we'll subtract the other term to the other side. So we've got this. And finally, we want to solve for the mass of the water. So let's divide both sides by this term here. Of course, these cancel out. We're left with the mass of the water. And in fact, since the specific heat for coffee and water are the same, those will also cancel out. And we're going to be left then with this. Mass of the water going to be equal to minus mass of the coffee multiplied by the change in temperature of the coffee divided by the change in temperature of the water. Now the mass needs to be positive, right? So if we've done everything right, we should come up with a positive mass. So the coffee's mass, we're going to put a minus sign, and then we're going to have 0.145 kilograms for the coffee mass. And for the temperature change for the coffee, delta T, it's negative 29.5 degrees Celsius. And for the water, it's 42.2 degrees Celsius. And now those negative signs are going to cancel, leaving us with a positive value of kilograms. Put that into the calculator, and we get 0.101 kilograms. That's the mass of water that we needed to add to cool it to that temperature.